Welcome to Machine Learning for Engineering and Science Applications. This is the first video for the course. So, in this course we will be looking at in this video we will be looking at the introduction to the course and a brief history of artificial intelligence through the ages. So, let us look at a few things that we are using that are essentially products of machine learning in real life today. We have seen Amazon's recommendation system. You would have had several such things using other software or other websites also. Basically, you buy a bunch of stuff of this website and it recommends other things, maybe books, other books or other products that you might like. This is Amazon's Echo. It is effectively run by a speech recognition engine combined with website searches. We have been all using Google's spam filter or any other company's spam filter, but Google's works really well. As a part of our mail system, it works very seamlessly nowadays. This is Google's Lexus, which is a self-driving car. So, now what is common between all these four is essentially all of them use as an essential part of their algorithm machine learning algorithms. Okay. So, machine learning, very simplistically speaking, is a method or a set of algorithms that you can use to replicate activities typically that require human cognition. So, for speech, humans recognize speech very well, starting from a baby to an adult, we do it very quickly. We all drive, those of us that drive fairly seamlessly. Spam filter, most of us can look at a mail and almost instantaneously say whether it is spam or not. However, in practice, in order to encode it into an algorithm is actually a difficult task, because the number of rules expands very rapidly. You cannot say that a mail, if it comes from Nigeria, is definitely going to be spam. If it involves money, it is going to be spam, etc. So, there is no finite set of rules that you can make, but nonetheless you would like a quick spam filter which works as well as a human being does. So, in such circumstances we tend to use a large basket of techniques. These are called machine learning models. These are very old models, several of them are at least half a century or even sometimes even a century old. So, we will be looking at many of these algorithms, but as far as this course is concerned, this course, the course of machine learning, can be a part of electrical engineering, it can be a part of computer science, it is a branch of mathematics. We are going to treat it as if it is going to be primarily used for engineering and science applications. Just to give you a couple of applications in mind, when you have an X-ray or you have an MRI that a radiologist looks at and starts giving you a diagnosis, okay, there is a tumor here or this is cancerous, not cancerous, etc. Can we replicate this sort of process using machine learning algorithms? Just like we are able to replicate driving, can we replicate this kind of judgment? Dr. Ganapathy, for example, is an expert in this field. Another application could be, we will see this in the middle of this course, that this is actually flow past a cylinder. So, what we are trying to predict in this thing is, if you have a circular body, a cylinder in this case, kept within an external flow, it starts giving what you see here are velocity contours. Traditionally, even today, we use several software and the whole process is called computational fluid dynamics, often abbreviated as CFD. You might use solid mechanics modeling or any continuum based PDE based modeling. The question is, can we find out models that can do this more rapidly using machine learning, and we will see that indeed a part of it is possible and this is an exciting field. So, our aim in this course is the following. First thing is, we want to understand basic machine learning models, okay, thoroughly. In specific, we are going to look at what is now very popular, deep learning. We will see what it is even later on today. Machine learning models thoroughly, and in particular some very fundamental models that have been used for almost 50 years now, okay, at various stages of development. We will also look at some modern machine learning techniques which have caught on as of the last decade or sometimes even as recently as last few years. We will be looking at several things that have been done in this field even in the last year. The field is moving very rapidly. We will look at it in the context of engineering applications mostly. Okay. And finally, what we want to do is to apply these techniques hands on to problems in engineering. Now, within a video course of the sort that we are teaching right now, there is only so much that we can do. We will look at some basic coding paradigms, we will also show you some examples, but the hope is you are self motivated and you do learn and program in Python by yourself. We will give you the basic rudiments and we will give you several basic examples, for example from medical image diagnosis, from turbulence modeling, CFD computation, etc. But our expectation is that you will also do some work on your own, okay. Whether you do the course for credit or not, you can get the maximum out of this course in case you tend to code yourself. So, we also hope that at the end of this course you should be able to read and understand research papers in machine learning, especially applied research papers. You might not be able to understand very hardcore machine learning theory, but if somebody has applied machine learning to some practical problem, hopefully you will be able to read a paper and understand it. This is also a primary aim of the course, because most of the development that is happening today is not necessarily present in textbooks, etc. It is mostly available as research papers, especially on archive. So, our hope is you should be able to get this also. So, this is the broad course aim. Okay. So, it intersects with other courses on machine learning, but the emphasis is a little bit more on the application side and getting an overview and getting basic idea of the models that are in play. Okay. So, in terms of prerequisites for the course, what is it that you require in order to make sure that you can complete the course successfully? One of the primary requirements that you would have is mathematical sophistication. This sophistication is a vague term. What it means is that you are comfortable with mathematics, thinking about things in a mathematical framework rather than just thinking of it in a vague framework which is just qualitative. We would like you to have a quantitative mindset. Okay. While we will be introducing ideas from whatever essential ideas you need, not the whole of linear algebra or probability or optimization for that matter, but we will be introducing you to some basic ideas that are required for the course. Okay. Nonetheless, that portion will be 1 week each, but more importantly you must be comfortable. Okay. Whenever we talk about something in mathematical terms, especially when it comes to probability, you should be comfortable in thinking through these things in a mathematical framework. That is one. Similarly, slightly similar in this respect is you should be comfortable with programming. Hopefully you have written programs at least in some language. We will be using examples from Python, examples from MATLAB. So, we expect you to be able to at least understand syntax from Python and MATLAB, but you will get the maximum out of the course if you are actually comfortable with programming itself and you can do some hands on exercises. We will be giving suggested exercises throughout this course. So, hopefully you should be able to do these, especially if you are trying to take the course for credit. Okay. So, here is an outline of the course. So, we will have 3 broad parts of the course. The first is artificial neural networks and deep learning. This includes what are called CNNs. CNNs are convolutional neural networks. These are used for vision. RNNs are used for typically sequential data. So, we will be using RNNs, CNNs as well as what are typically called simple ANNs, and this is the first part of the course. The second part of the course is other classical techniques that have been used for a long time. They are still applied in various areas depending on the complexity of the problem: tree based methods, support vector machines, probabilistic methods, etc. This is the second part of the course. Finally, we will look at some modern techniques such as generative adversarial networks, etc., and reinforcement learning if time permits. As far as applications are concerned, within each module we will discuss various applications for each of those modules as we go forth during the course. Okay. So, here is the syllabus for the course. This has announced on the website also. So, the first 3 weeks essentially are the basics, okay. So, are the fundamentals that are required for the course. So, the first week we are going to look at linear algebra primarily, then the second week will be probability and statistics, whatever basics are required. Obviously, that is a whole course in itself, but just whatever basics are required for this course. The third week would be whatever numerical computation and optimization basics you require, and also popular machine learning packages that are available today. We will look at an overview of those. Week 4 and 5 is essentially neural networks. So, it is possible to think of even linear regression as a very simplified neural network. So, we look at linear regression and logistic regression, these are the two basic algorithms, the simplified algorithms, then complex neural networks and multilayer neural networks in the next couple of weeks. The next 3 weeks are essentially variations on neural networks. So, this involves convolutional neural networks, this is for vision. Vision based problems are usually solved using convolutional neural networks. Recurrent neural networks are typically used for sequence based problems. Okay. So, sequences that develop in time, for example. So, time series analysis in some sense can be used using recurrent neural networks. Then we look at classical techniques that have been around for a long time and they are still used in conjunction with deep learning and neural networks. Some probabilistic techniques also we will be covering here, for example, Gaussian mixture models, etc. Okay. Unsupervised learning will also be covered here. Finally, we will look at some advanced techniques. There might be some changes here as we go forth in the course depending on how students are doing. So, we can also add a reinforcement learning if time permits towards the end of this. The reference books for this course, the first is by now, even though this is published only in 2016, it is already treated as if it is a classic text. It is a very good text called Deep Learning by MIT Press. Goodfellow and Bengio etc. are all researchers in the field. The second is Pattern Recognition and Machine Learning. This is also a very good text, though it is a dense text. It is a little bit harder to read, but it is an exceptionally well written text, very thorough text by Christopher Bishop. And the third is towards the practical implementation side. Of deep learning. This is by Francois Chollet. It is called Deep Learning with Python. Now, fortunately, the first two texts are actually available for free. Okay. These have been made available by the publisher themselves. This is legal. You can search for these texts and you will find websites where these books are being shared by the publishers themselves. I would very highly recommend that you go forth and take a look at it and also read through these texts as the course progresses. Okay. Please use the resources that have been generously made available by the publishers. So, we are really grateful for them to having done that. Okay. So, now let us look at a history of artificial intelligence through the ages. The idea of artificial intelligence has been around for a really long time. It is almost as old as whenever we started making tools. Why is it that we are covering it? One, to see that many of the ideas that we are covering are actually quite old. Also to see the ebb and flow of ideas. Okay. When ideas go up, when they come down, and some of the ideas we might be covering in this course right now might suddenly become unpopular for 5-10 years, but suddenly might become popular again. So, it is a good idea to know where a topic comes from. So, as I said, history of artificial intelligence is really old. Humankind has been fascinated with tools. They have been fascinated with what we can do. By looking at our hand, we have started looking at what kind of machine tools can I make so that I can replicate the motion of my hand. So, similarly, just like we have been thinking about mechanical tools, we have also been thinking about thinking tools. So, can I not only replicate whatever motions I am making, the wheel for transportation, the hand for working, the lever for lifting, etc., not just that, but can we actually make tools that can ease our thinking. This is Raja Bhoj of Parmar, this is from Bhopal. So, this is speculation. I do not want to say that he actually made a machine, he did not. So, within his works, Raja Bhoj was a very accomplished person, a poet, an engineer, he has a fantastic civil engineering work, all sorts of things. He also speculated that you could have robots that imitated or replicated human speech and motion, and even before him and after him there have been several people throughout the world, in Greece, in Rome, etc., who have been doing this. There were realistic automatons in several parts of the world, right from prehistory till date. One such example, though it is a fake example, is what is called the mechanical Turk. This was a claim by essentially a con man that he could make a machine that could play chess. What he actually had was a person inside, a person who could play chess inside, but nonetheless we know that there were several automatons, that is things that could move automatically, okay, and replicate at least human motion. Now Leibniz, he is also the father of calculus along with Newton, had a idea of a calculus of human ideas, okay. We will come to this as we go on later, but Leibniz's idea was that every thought that we have is a combination of a few axiomatic simple basic units of thought. We do not go that way, but you can see an analogy with how modern machines are working. How do modern machines work? Modern machines or modern computers work on the basis that everything can be broken down to zeros and ones, okay. So the basic question that machine learning people have been asking in a very broader sense is to see whether all that we do in terms of thinking, in terms of creativity, can it be broken down into a few elemental products, a few elemental processes. So Leibniz's speculation was this is indeed possible, okay. Charles Babbage made the first, or at least conceptualized the first analytical engine. Modern day computers are very similar to whatever Babbage actually conceptualized. This was right back in 1837. The fructification of this was in 1940s when the first computers were made. My point is, whatever we think of computation today, it is actually amazing. If you even read works from the 1940s, they could not have conceptualized what computers are doing today. In some ways you can even think of computers today as artificial intelligence, in that you can book a ticket, you can record speech, you can play music, you can see movies. This is a wide variety of tasks, mind you. All of those are done on one single humble computer. In some sense this is already artificial intelligence. What we are going to do, at least in this course, is a little bit further. We know that while this is going on, it is not really thinking, it is not really learning. Our idea is to see if we can make algorithms which can actually learn. So here is the birth of artificial intelligence. 1914 was the first chess playing machine. All it was doing was king rook and king ending. Those of you who know how to play chess will know that if one party has a king and rook and another party just has a king, you can checkmate always. So here was a machine which would actually do that, okay. Surprisingly enough, the first driverless car was right back in 1925. This was made with the help of the US Army, and I think Francis Houdini. This is not Houdini of the magician frame, this is a different person altogether. So he made the first driverless car. However, this was radio controlled, okay. Even this was quite amazing to people right back then. Now the first theoretical progress happened in the 1940s. We had the first artificial neuron. We will see this when we come to neural networks. Turing also first proposed the idea of theory of computation and the idea of a universal computer. The idea of a universal computer is the idea that one single computer can do all computable tasks. This seems obvious to us, we have sort of grown used to it, but it was not obvious right in the beginning that every single computation can actually be done, okay. You can think of ticket booking as a computation, you can think of playing a video as also a computation. All of that can be done on a single universal computer was not obvious at all. So Alan Turing was the person who actually pioneered this idea. Shannon also came up with information theory. This is now also being used extensively within ideas in machine learning, and of course in a lot of places, signal processing, etc. 1950s was in some sense a place when artificial intelligence took off, whether you read science fiction from that period or whether you read just normal research people writing. So Norbert Wiener came up with this idea of cybernetics. It was very popular. Minsky is a very famous researcher in this field. He made the first neural net machine, stochastic neural automatic reinforcement calculator, a SNARC, It was and Simon and Newell, Simon is a Nobel Prize winner, worked for all his life on decision theory and effectively artificial intelligence, what we call artificial intelligence today. So, they made an automatic theorem proving machine. So, the first machine was, this was not software, but it was actually hardware. The first neural network machine was made by Minsky in 1950s. 1956 was the first coining of the term artificial intelligence. A famous conference called the Dartmouth conference, Simon, Newell and Shannon, all three of them participated in this, and the sentiment was really positive. Rosenblatt was the first person who came up with a 2-layer artificial neural network called the perceptron. He unfortunately died really young. I think he died in the 1960s at the age of 40ish or something. Okay. Now, another researcher, Arthur Samuel, just to define machine learning a little bit more precisely than we did in the beginning, is to say that machine learning is the field that gives the computers the ability to learn. This is what is key, the ability to learn. We will define learning itself a little bit later, without being explicitly programmed. Okay. So, we will come to this distinction shortly. Okay. So, here is the idea of being explicitly programmed. This is the idea of an expert system. So, let us say you want to find out or you want to make an algorithm that detects grammar errors. Okay. So, some way to say it is, you start putting all the rules that you know of English grammar, let us say, into the machine, saying, you know, if this follows that, you know, if it is a singular person, then you put is, if it is multiple people, put are. But what happens shortly is, in many cases it is really hard to program all the rules, and we will see some examples as we go on forth. You will see that it is actually quite hard to do it even in grammar. It is not quite clear how it is that human beings are able to recognize different grammars for different languages. Most of us in India speak at least 2 to 3 languages, and most of us can seamlessly switch from the grammar of one language to the grammar of another language, and it is not clear what sort of rules we follow. So, expert systems work well when the rules are clear, and when the rules are not clear is typically when we would like to use machine learning. Okay. So, when in 1960s, when people thought of artificial intelligence, mostly they were thinking of rule based systems. Even in chess, for simple games like tic-tac-toe, you can usually quickly give the rules that will let you win or at least not lose. But in more complex games such as chess or Go, it is actually hard, and that is what people have been finding out. So, but early days of artificial intelligence, whether it was playing chess, making organic chemistry models, solving word problems in algebra, etc., even in understanding natural language, some progress was made, but it was not good enough precisely because of this, because of the fact that these were completely rule based. You had a rule for every single case, and if you did not give a rule, the computer does not know what to do. Okay. There was also theoretical progress. We will see this algorithm is what makes machine learning algorithms, or at least neural networks, learn. Back propagation, this was available way back in 1969, that is nearly 50 years ago today, okay, in 2018. But the progress was good and people were very optimistic. Here is Herbert Simon again, he is a Nobel Prize winner, as I said. He thought that machines would be capable by 1980s of doing any work a man can do. Unfortunately, till today machines cannot even do what let us say mosquitoes or rats can do. So, we are nowhere close. Nonetheless, we have made a lot of progress, which is why the course is here. Okay. We also had Minsky saying something extremely positive, which was very similar. Okay. But whenever you have such kind of a hype cycle, you should always know that you are going to get into problem. So, what was known as the first AI winter happened between 1974 and 1980. The problems were that all the results that were there, even within chess, were primarily for simple toy problems, the kind of exercise problems we do in any course, simple problems. The computational power was also exceedingly low. Today's cell phones probably have greater power than most of the big mainframe machines had back then. So, the computational power we are looking at in those days was really low. Combinatorial explosion, especially for rule based systems. Okay. So, like I said, there is no simple finite set of rules within which you can explain every single case of grammar. Okay. It is really difficult. Even for chess you cannot give a rule for every single situation, it is just too expensive. Combinatorial explosion means when you go from a small problem to a larger problem, the number of choices which are expanding is really large. If I only have a knight rook knight ending, I have only 3 pieces, that is slightly less complex. If I have 5 pieces, you have things start growing in terms of factorials, in terms of power loss, and that is very hard for a computer to handle. Okay. So, the key to even modern day machine learning is this idea that common sense is nearly impossible to program. A baby today can look at a face and recognize that its father or it is its mother, but to actually program in and to say why it is that this is its father, why it is that it is the same person regardless of this person changing their clothes, changing their expression, changing the way they speak, them growing older, having a beard or not having a beard, it is nearly impossible for you to program every single case in, but somehow magically human beings tend to do this really rapidly. Okay. So, how is it that this happens is, of course, it is a long standing problem in cognition, it is still an open problem. Nonetheless, we do know that it is nearly impossible to program this explicitly, that is, at least when we have rule based programs, you cannot do this that easily. Okay. And in fact, you can probably be bold enough to say that you cannot do it at all, which is where machine learning steps in. Now, one other thing that happened during 1974 to 1980 was Minsky's book Perceptrons showed up. He made a very simple argument which we will make later too. This was not an unknown argument. The fact that very simple neural networks which are called single layer neural networks cannot solve some nonlinear problems. It is kind of obvious, as you will see later on in this course, it is a very obvious argument. He also made an argument that multilayer neural networks are hard to train. Okay, so, that was also made. What we mean by training is that somehow it is difficult to kind of automatically program, which is what we are going to go into in this course, that this is very difficult to do if you have more than one layer. If you do not understand the term layer, that is okay, we will see this later on during the course. Anyway, this actually set up a panic, but it probably set up a panic in conjunction with the fact that already results were hyped. Okay. And what happened was there was a lot of loss of government funding in AI, and obviously most of the research work stopped. Nonetheless, some brave pioneers continued, and as usual you have this kind of boom bust boom cycle that keeps on going on in many fields. Machine learning is just one example, and one boom was between 80 and 87. We actually had the first driverless car then. This was, if I remember right, this is by Mercedes, and there was huge funding, if I understand it correctly, about 750 million pounds were invested in driverless car right back then. Okay, and it did not come to anything as we know now. Now of course Tesla is taking over, even Google, Lexus, etc. There was a boom because primarily some businesses were using expert systems, popularization of back propagation, and as usual Minsky said that we are probably going to go into bust. It did happen. Between 87 and 93 the PC became very popular. You are not looking at large computation, but individual people are able to do small word processing etc. for their needs. They are not looking at grand aims like general machine becoming smart etc. Okay. Again there were brutal funding cuts. It usually precedes a long winter in AI. Now between 94 and 2000 people got a little bit smarter, and there was a long period of consolidation. Some of you might recall or you might know that in 1997 IBM's Deep Blue beat Kasparov in chess. This was still a rule based system, it is not a machine learning system. A machine learning system playing chess has come only last year, again by Google's people, called it is an extension of AlphaGo, I think it is called AlphaZero. So 1997 Deep Blue beat Kasparov in chess. Almost all stockfish etc., all chess engines that exist today are still rule based. Okay. There was also simultaneously development in theory, okay, including probability theory, information theory, optimization theory, good optimization algorithms which we will be using in this course. And of course, there was the stupendous power of Moore's law. Moore's law is the law that the number of transistors doubles every 2 years. Now an adapted version of that is we have sort of made it true. On the y axis here is the number of calculations that you can do per second per unit money that you are spending. So that this is a log scale. On the y axis you have a log scale, this is a linear scale, and you can see that you have exponential growth, okay, of computational power, at least computational power in terms of the cost it takes for you to do this. So integrated circuits are there. We are now predicting quantum computation, which is at least supposed to help, not necessarily in computation, at least in some types of algorithms it is supposed to help even for deep learning. Google and other companies have invested very deeply into it. We also have GPUs that allow much cheaper computation. So Moore's law in terms of growth of computational, exponential growth of computational power has really helped. So 2000 to 2012 I would call the quiet years, but they were quiet in terms of artificial intelligence, but there were very significant developments. The company Google was born. Not only Google, there were several search engines. Of course, Google used it really well and came up with good algorithms for that. What it helped in was there is a large number of searches, and when there is a large number of searches, there is a large amount of data. So the key thing for machine learning is very data hungry, as you will see, was the amount of data that subjected itself to statistical analysis and statistical techniques. This is what happened between 2000 and 2012. There was an internet boom. Once again, lot of people offering lot of products, lot of people offering a lot of data, images, videos, all these came together and you had a large database on which you could train. By train you will see what we mean later on in the course. Also we had NVIDIA come up with GPUs. These are very packed computational power horses, and we had specifically good results. A few brave researchers were continuing their work using deep networks. Another thing that people did very pragmatically was, instead of looking at some bold aims like a machine becoming intelligent on its own, you started looking at very specific outcomes. Instead of even saying stuff like, I want a machine that will recognize everything when it looks at it, which would be the computer vision problem, it would say, can I have a machine that can read a postcard and read the pin code? Okay, just in that case it needs to recognize only 10 digits, okay, 0 through 9. So such specific outcomes really helped in getting good results. That is what led to the boom. Even today you will see specific algorithms for vision, specific algorithms for natural language processing in a specific area. Instead of saying something that can read your mail and understand it, can I have a spam filter? That is a specific outcome, and in such cases you can actually find out which kind of machine learning model works better than the other. Okay. So this led to good, very good results and led to a positive growth of the field. 2005, once again we had autonomous driving for about 135 miles, of course without any interruption. What people are trying for now is more sophisticated. Can you actually drive in a street while people are moving around, and we have had good results with Tesla. Also one important result, I think this was in 2011 or 2012, I am not sure. IBM's Watson beat the Jeopardy champion. This is a quiz show and it is a non-trivial quiz show. It is not a simple language show. It has puns, it has plays on words. So the machine needs to understand more than have a human sense in some sense. Okay. And after this period of consolidation, we are now within what would be called AI spring. We do not know whether it has ended. Some people are already saying it is ended, but anyway we all of us know that we are on a growth cycle right now. Okay. There has been a lot of what has sort of pushed it is a lot of private funding, not just government funding. In fact, governments are catching up. Google has its DeepMind, IBM has its own thing, has its Watson, Facebook has its things, Microsoft has its things, and all of them have been fairly democratic about sharing their resources also. There has been rapid growth in computational power, as I said earlier, GPUs etc., and a very important portion of it has been rapid growth in data. We know Facebook has data, Google has data, Microsoft has our data, and they have been doing a lot of data mining. legally hopefully, and this has led to a lot of growth in machine learning itself. A lot of people have done voluntary distributed work in, let's say, tagging images. Some of us have done it even though semi voluntarily using captchas. Captchas are this things, you will have digits like n, 1, 2, 3 etc. That's just popped up in order to identify whether you are a human being or a robo. But what it has done, it has also helped machines being trained. Each time you say this, a machine recognizes that this kind of image probably means n, this kind of image probably means 1. So, that is being used also in training. So, voluntarily and semi voluntarily we have been doing a lot of training for these machines, and that has led to a lot of data. Games also have led to a lot of data. Now, the inflection point, the point where a lot of people identify as the real growth of machine learning and AI, at least the modern boom cycle, is sometime in 2012. There is a challenge called the ImageNet challenge, which we will see later on when we come to CNNs. So, this is just a vision recognition challenge. Out of 1,000 categories of images, you have to say which one is which. Is this a cat, is it a dog, is it a building, etc. So, most of the algorithms at that point, all of the algorithms at that point which had been winning were in some sense traditional vision based, rule based algorithms. So, 2012 was the first time that a machine learning algorithm called a convolutional neural network which won. This is called, the algorithm which won is called AlexNet, which we will be covering in detail later on in the course. This was 2012, and since then every single year the algorithm which has won is only a machine learning algorithm. AlexNet showed a huge jump in performance based on about a 12% jump from previous algorithms, and this is when people sat up and took notice, and since then the field has just taken off very rapidly. The number of people who have got in within the last 5 or 6 years is just huge. People who started out doing their PhDs in 2012 without a machine learning algorithm have done things that have surprisingly changed during the course of their PhD. This is not very long, but a lot of the material that we will be covering in the course will actually be from the last 3 or 4 or 5 years. We will be covering classical techniques, but we will be also covering what has been specifically done in the last few years, which is another reason that we are keen that you also understand how to read research papers, because the field is still developing, it is still in some sense early days, and you need to know how to keep up with the literature. So, part of the language and the techniques that we will be introducing you through the course is for us to make sure that you can actually read the papers, understand them, and maybe implement them yourselves in some application of your interest. So, here are two results that have been the reason for people getting kind of worried. This is the machine versus humans. This is the same thing, Jeopardy. This is a quiz show in the United States. I do not believe this is there in India as yet, but it is a quiz show, and it is an involved language based quiz show. Of course, it is knowledge based also, but there are puns etc., and you have to understand allusions very clearly. So, the thing that won was IBM's Watson, and it is a machine learning based algorithm, or at least semi rule based, semi machine learning based. Another thing that was frankly a shock for many people in the field was AlphaGo. Go is a game which has simpler rules than chess, but it is known to be combinatorially much more harder to solve. It is a 19 by 19 board where people simply place a white or a black piece, but nonetheless it was often known to be a AI hard problem in AI. That is, chess was thought to be essentially solved by a rule based system. People thought that there would be no machine which will beat a Go champion in maybe another 10 years. Even Google, when they came up with AlphaGo, were not sure that they would actually win. Their aim while playing Lee Sedol, the Go champion at that point, was simply to maybe win a game or two, and then to learn and make their system better, but it actually beat Lee Sedol hands down. And after that, I think they have retired AlphaGo because it just has been so good in beating every single human being. Okay, it practically is unbeatable at this point. So, one thing that is also true about machine learning algorithms is sometimes it is hard to know how good they will be. So, these are two of the recent results, and they have been cause for again a recent hype cycle. So, the question is there anything different this time, and the answer is yes, at least there are a few tangible things that are different this time. We genuinely have better technology, and the computational power that is available today is exponentially huge compared to the difference between, let us say, 1950s and 1970s between two cycles. So, we have GPUs and we have all sorts of futuristic computational technology that people are proposing. Whether they come through or not, Moore's law is still holding its breath, and it is kind of running its course already. It is going forth, but we have different architectures. We have really big data, we are practically drowning in data, and probably we need better algorithms to handle this kind of data that we have. An important portion of the current boom cycle is we have had democratization of resources. A lot of people have, a lot of algorithms can be run on a simple laptop that is accessible to most people today. Between a 75,000 rupees to a 1 lakh laptop can actually have a simple GPU, a simple card that can actually do a very good job, and even some of the simpler algorithms can work. Also, many of the commercial companies have been very generous with their software. All the packages, whether it is Google's TensorFlow, Facebook's PyTorch, etc., IBM, Microsoft, all of them have made a lot of resources available to the common public. So, the open source movement has also taken off, and this has led to a lot of software which has been available to the common public. We will be using a few of these through this course, which actually makes a person come up to speed very quickly. Even if they do not know how to code something from scratch, they can use existing packages and at least use a few of those algorithms. We will be seeing that later on in this course. And there have been genuinely better algorithms, even though if they are variations of prior algorithms, we do genuinely have better algorithms today. So, our focus for the rest of the course is the algorithms portion. What we are going to really look at is what algorithms work and are under what circumstances do they work. We are going to look at algorithms as if they are models. So, if you have done any engineering problem at all, you will know that for sophisticated processes we have various models. If you are in fluid mechanics, you will have various models of how a fluid behaves, you will have various models of how turbulence behaves. Similarly, if you are in solid mechanics, you would have seen various models for how a stress strain should be modeled, etc. In every field, an ideal gas law is a model. Ohm's law is a model for how current and voltage and resistance play together. So, all these are models. We think of algorithms as if they are models. Modeling what? The specific input output relationship in any problem that you are looking at. So, suppose I have a mail and I am going to classify this as spam or not spam. So, there is something that is going on in my brain which is modeling this. What sort of model will work best is what we are going to look at through this course. Under what circumstances, if you have a vision problem, what kind of range of models do we have? If you have a time sequence problem, what kind of models do we have? This is what we are going to look at for the rest of this course. Thank you.